In this video, we're going to be talking about the classification and the organization of the periodic table of elements. So, the periodic table of elements is classified into groups and groups and periods. Periods move through rows and groups move through columns. So there are 18 groups in total and 7 periods in total. The periods represent the number of orbits there are. So as you can see, there's a maximum. An electron can hold a maximum of 7 orbits. Meanwhile, for the groups, it represents the number of valence electrons there are. So the valence electrons work differently for each section of the periodic table. So this middle part over here, these elements over here are called transition metals. To find the valence electrons and to find the regular electron configuration, you have to work in a much more traditional method, and we talked about that in a previous video. However, if you want to find the valence electrons for this part and this part of the periodic table, the way you can do it is by using the group number. So whatever group number it's located in would represent the number of valence electrons it can hold at a maximum. Okay. However, for this part, it's a little bit different. So you see over here that we have group 13, 14, 15, 16, 17, 18. Well, there aren't 13, 14, 15, 16, 17, 18 valence electrons. The actual way you figure it out is over here on the top. It has something like 1A, 2A. Then these over here in the middle from group 3 to 12, we have transition metals. So then this would be 3A, 4A, 5A, 6A, 7A, and 8A. So basically, the number that's located right next to the A would represent the number of valence electrons there are. So you can see in this group, there are 2 valence electrons, this group 1 valence electron, this group over here 3 valence electrons, 4 valence electrons, 5 valence electrons, all the way to the 8 valence electrons. This is just a simple trick so that you can get the number of valence electrons easier. However, this does not apply to the transition metals or the elements located from group 13 to group 12. So another way you can classify the periodic table of elements is through blocks. Basically, depending on the valence electrons, the number of valence electrons the element has, it also depends on what kind of block it is. So in a previous video, we explained about electron configuration and subshells SPDF. So that's actually how we're going to be doing it. The S block, the D block, the P block, and then the F block. So if you're wondering how that can work, look at this top picture over here. So basically, when doing the valence electron configuration, let's just take oxygen for example, okay? So if we were to take oxygen for example, it would have 1s squared, 2s squared, and over here, since 1, 2, that makes 4. So then you have. So if you're wondering what I'm talking about, you can just go to the valence electron configuration place, okay? So this is for oxygen, and you can see it ends in the subshell P. So whatever subshell it ends in is basically the block it's located in, okay? And over here, this is ending in subshell F, subshell D, this ends in subshell S. I'll show one more example, and we're going to be using magnesium for it. So I'll show you 1s squared, so this is 2 valence electrons, and then 2s squared. These are 2 electrons already over here. That makes 4. And you can see it is located in the S. It's located in S subshell. And because it's located in S subshell, the last one is located in S subshell, we find it in the S block. For this one, it's located in the P subshell. For the last one, so we find it in the P block. Let's just take zinc, for example, which is 30. Oxygen, magnesium, zinc. So 1s squared, 2s squared, so that's 4, and then 2p, and it's 6 because that's the max, so that's 10, 3s squared, 3p, 6, 4s squared. Okay, so we look over here and we can see the last one is D. And because zinc over here, it's located in the D block, that would make perfect sense because the last one over here is located in subshell D. Hence, located in the D block. And you could basically do the same thing with these elements, lactanoids and actinoids, and you would still find that the last one would be in F block. So that's, or the F subshell. So that's why you would do it. So another way is through color coding. So I'll just color code it. This part over here is our S block. So not only does it include hydrogen, but it also includes helium, which is on the other side over here. That is because when doing the electron configuration, we of course see it's just in the S block, so that's why. I'll even show you. So like, it's just in 1s squared. See the number of valence electrons, and then 2, which also has the number of valence electrons, and we see it's in the S block. So yeah. Next, we would go into our P block. This over here is our P block. This basically concludes that all the elements located in this certain location of the periodic table will have the valence electrons to where it'll be located in a P subshell. It'll end in a P subshell. Then we will have our D block. This tells that all the valence electrons located here will be located in the D subshell. The last electrons to fill are in the D block. It doesn't necessarily have to be a valence electron. It's like, so if you're confused about zinc for a second, you could see that 4s comes before 3d, but we know 3 comes before 4, and it's because the energy flow of the electrons moves in a certain pattern. And if you just look at that previous electron configuration video, you would understand why. So if you look at zinc, the last one to fill was the D block, so that's why it's located in the D block. And then lastly over here, we have our F block.